Good morning, everyone. So a brief introduction about myself. I'm a research professor at the Institut National de la Recherche Scientifique, where I lead the electrochemistry and microenergetic system laboratory at the Energy Materials and Telecommunications Center located in Varennes. My research activities covers materials to devices for energy storage, such as rechargeable batteries, supercapacitors, and also we have activity for energy conversion devices like fuel cells, specifically alcohol fuel cells. Other activities we cover are bioelectrochemical fuel cells as power sources for implantable medical devices. We have also some research going on related to electrochemical biosensors for the detection of glucose and diabetes monitoring. So I'm not sure if I have enough slides to cover 30 minutes, but let's see. I would like to thank the organizers, the conference organizers, for their invitation and for giving me the opportunity to present our advances in the development of energy storage systems. Specifically, the talk is about rechargeable zinc-air batteries, systems which are of increasing interest to researchers and industry. My talk will not focus on scientific and technical details, but rather on the general aspect of the zinc-air battery as possible candidates for next generation energy storage. I would, however, show some progress in terms of the development of these systems that are carried in my laboratory. So allow me to get straight to the point. So electrochemical devices such as batteries have and will continue to play a key role in our modern society, as they are widely used as energy power sources in various sectors. Lithium-ion presently dominates the landscape of rechargeable batteries, especially for portable devices, small domestic appliances, electronic gadgets, electric vehicles, and some stationary applications. I don't know if you can see the slide clearly, but this table shows that Canada ranks 6th in the world in lithium reserves and only account for 0.4% of world production in world production. So Canada, therefore, remains far from major countries with lithium reserve production. The large-scale demand for lithium, its high uneven geographical distribution, and its rising price call for the development of alternative batteries or complementary batteries to lithium-ion batteries. This plot, for people who are familiar with the energy storage and conversion systems, academics or industrial, they are familiar with this plot, which is called the Ragon plot, This is a graph that compares performance of various energy storing and conversion devices where the value of energy density in watt-hour per kilogram are plotted versus the power density in watt per kilogram. So the energy density here is the measure of how much energy a battery contains in proportion of its weight, more specifically, it's the quantity of energy able to be stored and restored during the operation of a battery. As can be seen in the diagram, zinc-air battery are, I don't know if it's not working, but zinc-air battery are located at top left as they have relatively high energy density. Times shown in the plot are what you call the discharge time. They are obtained by dividing the energy density by the power density. So if you're not familiar with the term discharging or draining, that term describes the process of a battery losing voltage or energy. And the power density, on the other hand, refers to the rate at which energy can be delivered or extracted from the battery. So a brief history of metal air batteries. As you can see in the slide, the invention of zinc-air battery was one of the battery invented in 1878, and then much progress has been made in the research on metal air batteries. So the first battery was used as, it's non-rechargeable, this is why we call them primary batteries. It was used mainly for hearing aid systems, okay? But there are a lot of work after that regarding metal air battery. So what about zinc? Well, zinc in the world, okay? For that, okay, I just would like to show this. This is another chart that compare the theoretical energy density, theoretical cell voltage, and cost of metals for different metal air batteries compared with the lithium-ion battery. As you can see on the chart here, among various battery types, metal air batteries hold great promise for future energy applications. So, because they offer the highest theoretical energy density among all rechargeable battery types. And this is due to the use of oxygen in air at the cathode, enabling a significant reduction in cathode size and the overall weight of the battery. So, of course, as I said in my presentation, the type of battery we are interested in are zinc-air batteries, whose energy density is over 6 times higher than lithium-ion battery, meaning that they can store more energy in smaller space. So this makes them more efficient and capable of powering, potentially capable of powering electric vehicles for longer distances. It is also important to note that the cost of zinc is almost 5 times cheaper than that of lithium. The other metal air batteries, of course, they have high theoretical energy density, but in terms of research and development, there are very serious problems to tackle. For example, the lithium air battery. So this is the second in the chart. Lithium-ion battery have major limitations, such as higher cost, of course, because of lithium, an unstable anode, which is lithium. It reacts with the electrolyte, and it has also some safety issues. For the aluminum and magnesium batteries, okay, researchers observed some rapid corrosion that happens in aqueous electrolytes due to more negative electrode potentials. And this is why zinc-air battery are much interesting for us for the time being. So what about the zinc reserve in the world? So the availability of zinc is not a major problem compared to lithium, since the world zinc reserves is high and estimated to 210 million tons in this is in 2020, the last estimation. The other important thing about zinc, okay, is 100% recyclable. Okay, it can be recovered and reused without loss of quality. So currently, 30% of all zinc produced worldwide originates from recycled or secondary zinc. So this is very good advantages compared to lithium. And the world mine production, of course, the annual production of zinc globally is over 100 times that of lithium. So in Canada, there are some provinces like Manitoba, Quebec, Ontario, New Brunswick, and British Columbia, okay? They have some zinc production in metric tons. So, okay, you can see the number, okay? But it should be a table of 3 columns, anyway. North and West Territories, Yukon and Nunavut also. I don't have the data for that, but I heard that they will have their mines also for producing zinc in the future. So, if you're not familiar with the working principle of lithium-ion batteries and zinc-air batteries, what is the difference between these two systems? It's mainly the basic difference is in the chemistry. So I'd like to briefly, simplify how these two systems work. So for example, this is the working principle of lithium-ion batteries. The modern ones are based on what we call intercalation chemistry principles, which means the positive electrode generally uses lithium intercalation compounds, okay? This example is lithium cobalt oxide. Now we have in our phones lithium manganese oxide, for example, and there are other lithium iron phosphate, okay, also as cathode. So it depends on what company makes the batteries. So then it uses the negative electrode. It employs lithium carbon intercalation compound, okay? And the electrolyte is an organic solvent, okay, in which lithium salts are dissolved. And during the charging process, lithium ions de-intercalated back and forth, okay, between the two electrodes. So the type of electrolyte, you heard about the safety of lithium-ion batteries, you know, sometimes there is fire, explosion, and stuff like that, because they use the organic electrolytes, which are, depends on the type of battery, organic electrolytes such as ethylene carbonate, dimethyl carbonate, and diethyl carbonate. Sometimes it's a combination of the two or the three. And as salt, they use lithium phosphate fluorine for that. So this is okay, a simple description of the how lithium-ion battery work. What about inversely for the zinc-air battery? This type of system generates electricity via a redox reaction, which means you have two reactions, one is reduction and one is oxidation. And these two reactions happens between the zinc at the anode, which is the negative electrode, and the oxygen that's coming from air, okay, at the porous cathode, or what the air positive electrode. And these two reactions, with two reactions, the battery provides electricity on demand, okay? And so basically, when the battery is discharged, the zinc metal is oxidized, while the oxygen is reduced on the cathode side. And during the process of recharging, these mentioned electrochemical reactions are reversible, okay? And the active metal zinc being the only one, okay, to be stored in the battery, and the active component of oxygen being absorbed by the ambient air, which allows the zinc-air batteries to have high theoretical energy density. And I would like to recall that the intrinsic advantages of these batteries are the use of cheap and easily recyclable anode active material, that is zinc, okay? And the use of non-toxic, non-flammable aqueous electrolyte, which is potassium hydroxide electrolyte, and oxygen, which comes from environmental air as the cathode. And the other advantage, they have potentially very low manufacturing cost. According to the latest technology strategy assessment, the US Department is eyeballing new long-duration batteries that provide electricity, okay, for 10 hours and more. So for any type of battery, this is the goal, okay, or the objectives set by the US Department of Energy. And we believe that rechargeable zinc-air battery could fit the bill. Of course, life is not ideal in the lab when we develop materials. Of course, everybody knows that. We are very happy with the systems, but there's still some technical and scientific challenge to overcome in order to have one day this zinc-air batteries commercialized. And there are some problems, okay, from maybe 4 or 5 problems. Some of them are easy to tackle, but and the others we have to work more and harder for that. So I will just mention these problems briefly. There are corrosion problems, which is carbon oxidation when under high potential of oxygen evolution reaction. This carbon corrosion leads to the formation of carbon dioxide, which reacts with the electrolyte and produce potassium carbonate, which will clog the pore structure of the air cathode. So I have to tell you that the zinc-air batteries is a semi-open system, okay, that requires rich oxygen from the outer environment to participate in the reaction process. So there is CO2 also in the air, okay? So this is difficult to avoid, and this CO2 will enter the battery and reacts with the hydroxide ions in the electrolyte and make this carbonate precipitate in the solution. But this is not really a major problem for that. Another issue is the design of the battery is very important, okay, for commercialization. Designing the battery and its operating conditions will have significant impact on the longevity of the electrodes. So in the design of a zinc-air battery, it is essential, in this case especially, to understand the transport of and the reaction of oxygen in the air-breathing cathode. So we have to use some modeling, numerical modeling, which considers several parameters to design the battery itself, I mean the hardware, okay? So these are not major problems here. But the second two here, one concerns the lifetime of the zinc anode, okay, which happens that upon cycling of the battery, there are sharp needle-like zinc dendrite, as you can see here, that would develop on the electrode surface, okay? So this is actually one of our results. And these zinc dendrites, okay, can perforate the separator. There is a separator which separates the cathode and the anode, okay? Separator, and reach the cathode side, and this will lead to a short circuit and catastrophic failure of the batteries. Besides dendrite formation, there are also changes on the electrode thickness because zinc is oxidized, okay, during the operation, so there is more part of zinc that is removed, okay, sometimes. So this leads to change of the electrode thickness and the surface area, okay, can also be observed during zinc-air battery cyclings. So what is the solution? The solution for that, okay, we need to develop a new zinc electrode configuration capable of inhibiting the dendrite formations. Actually, now the zinc is we use just a zinc foil, okay? Simply this zinc foil. So we need to develop new formulations of electrode to avoid these corrosion problems and also zinc dendrite formation. Actually, we are working in our lab to solve this problem. Okay? So, but the biggest one, or what we call the bottleneck of the research and development, is the is the air cathode. As I showed you in the working principle of the battery, we have two reactions at the cathode side. We have oxygen reduction reaction and oxygen evolution reaction, okay? So these are two reactions happening, and for that, we need to develop a catalyst which has bifunctional properties, okay? Which means it's capable to reduce oxygen and also oxidize oxygen. And this is, okay, efficiently do that. Okay, so mainly now, most researchers in the world are working on these aspects, okay? Develop a catalyst with bifunctional properties. The state-of-art catalyst now, or the commercial one, are very expensive. They are based on platinum and iridium oxide or ruthenium. They are very expensive. They work very well, but also the target, as you saw, we need to develop catalysts okay, that are free of expensive materials. So we have to look for some idea. In the past few years, we have been working in our lab trying several catalysts which doesn't contain noble metals. and we designed several ones, and we recently, so we could, the optimal performance we obtained were with what we call self-supported cobalt or nickel-doped manganese oxide nanorods that are grown onto carbon sphere chains. And the image here is just photos from scanning electron microscope, okay? That shows the shape is sea urchin-like shape. So these were the optimal catalysts we developed recently, and we subsequently integrated these structures, okay, in homemade batteries we make in our lab. Of course, it's very archaic type. It's not the commercial ones. So we make these batteries using a computerized numerical control machine, which is, as you can see there. And fabricate the device. And the battery as itself here, its structure is very simple. It includes the zinc anode, okay, and the separator, which prevents contact of the two electrodes, and a reservoir of the electrolyte. And the cathode side, there is a hollow space is engineered to allow oxygen from air, okay, to access the electron. So these are very small batteries. The volume of electrolyte here is very small, 1.4 milliliter. Okay, so it's not huge. Okay, so when you study battery systems, okay, there are several electrochemical studies to conduct, okay, but when you're happy with the catalyst you develop, okay, it shows high performances, high current densities, and stuff. Okay, for the industry to commercialize the battery, the main parameter is the durability. Okay, the life cycle. Okay, for a battery. So the life cycle with our materials here. This is typical in battery studies. This is typical cycling, which are called pulse cycling, for certain time of discharge and certain time of charge at a current density. So of course, you can change this value when you study the performance. So the important here, for our materials here, there is high round trip, we obtained high round trip efficiency, close to 60% at 100 cycles, which means over 33 hours of operation, and we couldn't see any performance degradation. Actually, I have to say to you, 60% is one of the highest, okay, efficiency now for in Zinc-Air battery research and development. Okay. So if you want to know what is the round trip efficiency, this is defined by the energy, the ratio, sorry, of energy released during the discharge and the energy needed when recharging the battery. Specifically, the discharge and charge are at the same current density. Okay, you apply one value, and the round trip efficiency can be simplified as the ratio of voltage of discharge and charge. So it's very simple to calculate that. So, and of course, we have to compare with the commercial material, okay, the state-of-the-art material. So we made our electrodes with a mixture or a composite of platinum, iridium oxide, okay? And we did this cycle life of the battery using these materials. As what we observed, that during cycling, the voltage gap increased, and there is a rapid drop of the efficiency. Actually, it was 65.3% to 31.9% at 61 cycles, okay, over 20 hours. So this is very good news, okay, because our materials compete very well with the expensive or the commercial ones. Okay, I have just to give you an information. The standard voltage of Zinc-Air battery is usually less than 1.65 volt, okay? And however, the cell voltage is in practical is 1.2 volt. Okay, so when the battery are discharged at current density, if we use the current density from 1 to 10 milliamps per square centimeter. Okay, and when the battery are recharged, the voltage often requires 2 volt or higher. So still problems also with the because of the problems I just talked in the beginning. Okay, this affect we cannot reach for now the theoretical voltage of 1.65 volt. Okay, so it's also interesting to show how this material works for real applications. Okay, so in our lab we first checked some handheld electronic application. We see if our batteries can operate these systems. Okay, so in the left, on top of the left, this is just the measure of the voltage provided by the battery. Single battery provide 1.48 volt, and 2 batteries connected in series provide almost 3 volt. Okay, close. Then we use these batteries to power some devices. There is a 3 volt multimeter, okay, that was powered by our batteries, and it could measure a resistor as high as 10 kilo ohm. Another impressive results with the laboratory timer, okay, and we could operate that laboratory timer for 17 days, okay, without voltage loss. That's very good. The other application, which was we employed 39 red LED, okay, and also with the 2 batteries, okay, 2 small zinc batteries, we could operate these LEDs for about 200 hours. So that were very good news for us. There is another aspect we are interested in, of course, about hydrogen or green hydrogen. Okay, as you know, this represents one of the most promising energy carriers and the main energy carrier in the hydrogen economy in the future. Administrations around the world have started, okay, pushing the research, development, and commercialization of alternative hydrogen production pathways that emit little or no carbon dioxide. As more than 90% of hydrogen is currently produced from fossil fuels, as you know, which contributes to significantly higher CO2 emissions. So to produce hydrogen from renewable resources, what we call green hydrogen, one promising pathway is to split water, okay, into hydrogen and oxygen using electrolysis or photoelectrolysis, okay? So if you ask, if you are wondering why we have colors for hydrogen, okay, because hydrogen gas is invisible. So these are just color codes, okay, that are used within the energy industry to just differentiate between the type of hydrogens, okay? So depending on the type of production used, different color names are assigned to the hydrogen, okay? There is no green hydrogen or red one. Okay, so water splitting, okay, yesterday Dr. Samane, she talked about water electrolysis, so she gave good details. Another speaker also talked about that. So I will be very brief in this case, the water splitting, okay. So in electrochemical water splitting, hydrogen is formed at the cathode, as you can see there, via a reaction called hydrogen evolution reaction, and oxygen is formed at the anode via a reaction called the oxygen evolution reaction. So this type of system, there is 0 carbon dioxide emission, okay? And for now, the best catalyst for the hydrogen evolution reaction are noble metals, in particular platinum, whereas the oxygen evolution reactions uses iridium and ruthenium oxides. Okay, these are the best candidate materials for now. Okay, too, there has been a large push towards developing catalysts using what we call earth-abundant materials, because platinum, iridium, and ruthenium are scarce and expensive. In addition, it's also sometimes difficult to create water splitting using a system with different cathode and anode because different catalysts are active and stable in different pH ranges. So we were therefore interested in exploring whether our developed batteries can be efficient for water electrolysis. And indeed, as you can see on the left figures, okay, the left figure, our batteries effectively provide electricity needed to split water into hydrogen and oxygen. For test period, we conducted about 18 hours, okay? I must also further emphasize that for the reaction of water electrolysis, the anode and the cathode here, okay, as you can see, the anode and the cathode are made of the same catalyst that acts as cathode in the Zinc-Air battery, okay? So hence, the designation of a self-driven water splitting system. So we conducted tests for durability, okay, at current density as high as 30 milliamps per square centimeter for 20 hours, okay? And it shows that our catalyst, what we call NRS catalyst, competes very well, okay, with the expensive ones in terms of durability and also voltage. So you can see some bubble formation from the oxygen and hydrogen. So I will conclude end my talk here. I hope that I answered a little bit the question of the presentation, okay? And just to tell you that Zinc-Air energy storage system is getting hotter in terms of research and development. Just to remind some experts, okay, describe zinc as the electric fuel of the future. Its main advantages include its ease of charging and its high energy potential. The Zinc-Air battery gets a dramatic boost from low-cost material breakthroughs. Okay, we have developed low-cost materials, but other groups in the world are also working on this side. And the devices theoretically meet all required characteristics for next-generation secondary batteries, such as high energy density, abundance of zinc, low risk of explosion. It doesn't use organic electrolytes, okay? Eco-friendliness, okay? And low cost of materials. So we have patented these results, okay, last year, I think. So you can have access to these two patents. Okay, I'd like to thank the Zinc-Air battery team, hardworking and very smart members, okay, who worked on this project relentlessly. Some funding organization, and also our industrial partners, okay, we are working with us for, now we have a project with them for 3 or 4 years coming to complete the development of these air battery systems. So thank you for your attention, and I would be happy to answer any question in English or in French, okay?
Thank you so much. It was a great presentation. I just have a quick question regarding the commercial Zinc-Air battery, regarding the precious metal loading. Do you have any idea about the loading of commercial one?
The commercial ones?
Commercial one, yeah. Normally what is the
loading? I don't
recall
the loading, but it should be of the milligram order.
Okay.
Okay?
Okay, thank you so much. Yeah, thank you.
Thanks for, it's very interesting. What is the TRL, technology readiness level of the zinc battery?
Sorry, I couldn't hear. Maybe your microphone is closed.
Okay. What is the TRL, technology readiness level of the...
Well, TRL now, I think it's, we are between 1 and 4, okay, for now. Just 1 and 4 TRL. Okay?
How many years do you expect will be commercial?
Yes. So our target, at least for our group and our industrial partners, we have 4 years target. Okay, just 4. Yeah, 4 years target. Because I mentioned there are some. Sorry, you don't hear me. Sorry. As I repeat, okay. With our industrial partners, we have a target, okay, to develop these systems. We have 4 years target. Okay, they are investing with us. But there are, as I said, there are some problems to tackle, okay? Especially the corrosion problems, okay? The carbonate formation. And in the future, we're going to for a solid state electrolyte, okay? Mainly polymer ones, okay? Gel polymers, one, which like this, they are safer, more safer. We avoid these corrosion problems, but you can make them also flexible, okay? Flexible batteries, and then you will increase the range of applications for that. Welcome.
Bonjour, moi j'ai une question en français. Vous avez mentionné les problèmes, en fait les bottlenecks, si on veut, du niveau technologique qui reste à surmonter pour que votre chimie de batterie prenne plus d'ampleur dans les usages qu'on aimerait bien en faire en société. Je me demandais si vous sentiez que vous avez le bon support au niveau des politiques publiques pour être capable de mener efficacement votre recherche, de bâtir les bons partenariats pour que le développement se fasse le plus rapidement possible.
Qu'est-ce que vous voulez dire par les bons choix publics?
Ce que je veux dire, c'est est-ce que vous sentez qu'il y a les bons programmes en place pour faciliter votre recherche et développement, pour faciliter peut-être la collaboration avec les acteurs du domaine industriel qui pourraient contribuer à faire une économie d'échelle avec votre batterie?
Oui, nous avons des acteurs industriels qui travaillent avec nous sur ce domaine. Ils ont investi de l'argent, ils vont investir plus. Et comme j'ai dit tout à l'heure, nous avons un objectif de 4 ans, okay? Et nous allons déjà commencer, parce qu'on a breveté, okay, une partie. Donc nous allons déjà commencer à effectuer le transfert technologique avec les compagnies, et ils vont ouvrir une unité pour ça, une unité de batterie pour ça. Okay? Donc la compagnie avec laquelle on travaille développe comment on appelle ça, les piles photovoltaïques. Okay? Mais ils vont aussi ouvrir une unité de batterie avec nous. Donc, il n'y a pas de souci dans ça. Okay? Merci. Oui, Sébastien.
Oui. Merci, professeur Mohamedi. Sans révéler de secret, okay, sur les matériaux, et puis tu es un fin cuisinier pour transformer les propriétés des matériaux. Là. Tout ce qui est les bulles, tu sais, tu montrais des bulles qui restent collées sur l'électrode. Est-ce que tu as un peu structuré le matériau? Si tu montrais quelques images où on voyait des jolies formes de ton catalyseur, est-ce que ça, tu vas pouvoir le régler aussi pour justement régler le problème des bulles?
Oui, très bonne question, Sébastien. C'est l'application pour l'électrolyse de l'eau, on l'a fait très récemment, dernièrement. Okay? Donc l'étudiante qui travaillait sur le projet, donc je lui ai dit, ok, allons-y voir si on peut faire l'électrolyse de l'eau avec nos batteries. C'était donc à la dernière minute. Donc c'est très archaïque comme test, mais c'est sûr que si on veut développer cela pour l'électrolyse de l'eau, il faudra tenir en compte de la mouillabilité, okay, des bulles. Il ne faut pas que les bulles restent collées sur les électrodes. Okay. Donc il faudra redesign, comme on dit, un petit peu les matériaux de cathode et anode en jouant ou en modifiant leurs propriétés de surface. Okay? Donc les rendre peut-être plus hydrophobiques, okay, pour que les bulles d'oxygène ou d'hydrogène ne restent pas collées sur les électrodes. Donc on pourra récupérer l'oxygène et l'hydrogène d'ailleurs. Mais c'est le prochain projet de thèse. Okay? Thank you.
Merci beaucoup pour cette belle présentation ainsi que pour toutes vos réponses à nos questions. Votre question de départ était: les batteries Zinc-Air rechargeables sont-elles prometteuses pour le stockage de l'énergie verte? Une autre manière de formuler la question est de savoir s'il s'agit de candidates crédibles pour cette nouvelle génération de batteries dont nous avons besoin. Et votre réponse a été extrêmement positive. Dans l'ensemble, vous avez alterné entre les aspects, disons, plus scientifiques et techniques et les avantages plus commerciaux concrets de ces batteries, en donnant, il me semble, 4 arguments majeurs en faveur de ces nouvelles batteries. La première grande question qui amène à un premier grand argument en faveur des batteries R-Zinc est la question des matériaux qui sont utilisés de leur préciosité et naturellement de leur prix. On pensera ici par exemple au lithium qui est majoritairement utilisé aujourd'hui et qui pose tout un ensemble de problèmes, aussi bien sur des questions de sécurité que sur des questions de pression sur ce matériau critique, alors qu'un métal comme le zinc est déjà extrait en grande quantité aujourd'hui. Les productions existent déjà, les stocks sont conséquents. Il s'agit d'un métal qui est facilement recyclable. Donc il y a ici tout un ensemble d'arguments qui, disons, donnent un premier atout aux batteries air-zinc. La deuxième, disons, ligne d'argument vient de ce diagramme que nous avez présenté, le Ragon plot, je ne sais pas comment je traduirais ça en français, qui donne deux indicateurs. D'une part, la densité énergétique des batteries, qui est le rapport entre l'énergie qui peut être stockée dans une batterie par rapport au poids de cette batterie, qui pour toutes les questions de transport donne évidemment une information extrêmement précieuse. Et ici aussi, les batteries Zinc-Air ont un argument à donner. Le deuxième indicateur, c'est la question de la vitesse de décharge des batteries. À quelle vitesse est-ce que, alors deux éléments, est-ce que les batteries se déchargent naturellement et est-ce que l'énergie qui est stockée dedans est exploitable rapidement? Ici aussi, il y a un deuxième argument de ce type de batterie que vous défendez. Le troisième est naturellement une question assez fondamentale, qui est la question du cycle de vie, de la durée de vie d'une batterie. Et ici, alors que, donc, je vais dire que l'unité, l'indicateur intéressant est la question du rapport qui existe entre l'énergie nécessaire pour charger une batterie et l'énergie qu'on pourra réutiliser lorsque celle-ci sera déchargée, et notamment voir comment ce rapport évolue en fonction du nombre de cycles de charge-recharge, charge-décharge de la batterie. Et ici aussi, les résultats sont très prometteurs, puisque sur plus de 100 cycles charge-décharge, il n'y a aucune observation de baisse significative, ce qui est un autre argument important. Le quatrième que vous avez développé à la fin de votre présentation est la possibilité d'utiliser ces batteries dans un autre contexte, qui est le contexte de l'hydrolyse de l'eau pour produire de l'hydrogène, donc on pourrait s'en servir comme une forme de catalyseur dans d'autres domaines. Mais comme vous l'avez dit à un autre moment de votre présentation, la vie est généralement pas aussi facile que ça. Il y a toujours des sujets de recherche sur lesquels il faut continuer à travailler. C'est pour ça d'ailleurs, à mon avis, que vous étiez là également. Il y a tout un ensemble de problèmes. D'abord, un problème de corrosion qui est dû au rôle qui est joué par l'oxygène dans la réaction. Un deuxième type de problème qui est lié au fait qu'il s'agit de batteries en milieu semi-ouvert et qui peut amener tout un ensemble de problèmes, notamment si le CO2 vient interagir au sein des réactions qui ont lieu à l'intérieur des batteries, mais surtout le problème qui est le plus important, mais qui ne concerne pas uniquement ces batteries, mais toute forme de batterie, est le problème de trouver des catalyseurs qui fonctionnent à la fois à la charge et à la décharge et qui n'utilisent pas de métaux rares, précieux, sur lesquels il y aurait déjà ce qu'on pourrait appeler des matériaux critiques, sur lesquels il y aurait déjà une forme de pression. Donc il y a ici, on va dire, un champ de recherche encore pour le développement de ces batteries qui, en tout cas, proposent tout un ensemble d'arguments en leur faveur. Merci encore pour votre conférence.